Okay, let's dive right into this explainer and unpack the hidden physics behind literally one of the most exhausting household chores you will ever face. We're talking about moving day. You know the drill, packing up your entire life, hauling those heavy boxes, and lugging furniture up and down the stairs. It is universally dreaded. But what if I told you that by looking at moving day through the lens of physics, you can actually understand the fundamental mechanics of the universe? You absolutely know the feeling. It's the end of the day, you're sitting on a taped up box eating some takeout pizza, and every single muscle in your body is just aching. So, why does moving house leave you so incredibly exhausted? Well, today we're going to look at exactly what is happening to your body and your boxes using a foundational concept known as the work energy theorem. It connects forces to the transfer of energy, and honestly, it perfectly explains your moving day fatigue. All right, let's jump into section one, work, and specifically lifting those boxes. Let's start with the absolute heaviest, most dreaded chore of the day, lifting all those densely packed moving boxes off the floor. Now, in everyday conversation, work just means sweating through a difficult task, right? But in physics, work has a very strict mathematical definition. Work is only done when a force actually causes an object to move a specific distance. It's force times displacement, which is just the distance moved, times the cosine of the angle between them. Basically, if you apply a force and the object moves, you are doing work, and we measure that in units called joules. And this right here brilliantly illustrates the difference between everyday effort and physics-defined work. Imagine pushing with all of your might against a heavy, stuck, moving truck door. You're exhausted, you're red in the face, but because that door didn't move, because there is zero displacement, the work you did is actually zero. Compare that to lifting a heavy box off the ground. Applying force plus upward movement, that equals actual, scientifically verifiable work. Moving right along to section two, the no work horizontal carry. Okay, so let's grab some lighter bags from the back of the truck and head toward the front door. Now, there is a massive physics loophole here. Walking those bags horizontally into the house means absolutely zero work is being done on the back. I know that sounds completely crazy. You're carrying heavy duffel bags 30 feet to the door, and physics says no work is happening? How is that even possible? Well, it all comes back to our formula. When you carry a bag across the yard, your lifting force is pointing straight up to fight gravity, right? But your actual movement, your displacement, is horizontal, going straight forward toward the house. Because your lifting force goes straight up, but you're moving horizontally, the force is perpendicular to the motion. The angle between them is exactly 90 degrees. And in our mathematical formula, the cosine of 90 degrees is zero, which completely zeroes out the work. You're basically just coasting the bag along horizontally, not adding or removing energy from it in the direction of your lifting force. Which brings us to section three, power, and racing up the stairs. So, work depends strictly on force and distance. But what happens when we try to move those boxes up to the second floor? Enter the concept of power. Power doesn't just care about the work being done, it cares about how fast you're doing it. It's the rate at which work is done, calculated simply by dividing work by time. We measure this in watts. And just to give you a little real-world context, 1,000 watts is a kilowatt, and roughly 746 watts equals 1 mechanical horsepower. Let's put this into a real moving day scenario. Imagine you and your friend both grab completely identical boxes from the truck. You need to get them to the master bedroom upstairs. You decide to walk slowly up the stairs, but your friend decides to show off and completely sprints up the stairs. If you race your friend with identical boxes, you both do the exact same amount of work because the force and the distance are identical. But the runner generates far more power because their time is much shorter. A smaller number on the bottom of the fraction means a much bigger power output. Next up, section 4, energy. Essentially our moving fuel. You see, you can't do work and you certainly can't generate power without a source, and that source is energy. The work energy theorem connects all these ideas, defining energy simply as your overall capacity to actually perform that work. When you eat that slice of moving day pizza, your body stores chemical energy. When you lift a box, you use that stored energy and transform it into the work of moving the box. Energy exists in so many different forms, constantly transitioning from one to another, but it always boils down to that capacity for action. Now, at the secondary school physics level, we focus heavily on mechanical energy. Mechanical energy is the energy acquired by the objects upon which work is done. You can imagine mechanical energy as just like a tightly coiled spring, packed with the capacity to release force and cause movement. When you hold a heavy box at the top of the stairs, it has mechanical energy, specifically potential energy, just waiting to be released if you were to say, accidentally drop it. All right, let's wrap things up with section 5, the moving day pop quiz. Okay, we've covered the 3 pillars of moving day mechanics. Let's see how well you've packed up these concepts with 3 rapid-fire questions. Question number 1. You are pushing with all your strength against the side of the moving truck, trying to shift it over just a few inches, but the parking brake is on and it absolutely does not move. Are you doing any work? Think back to our definition of work and the required displacement. Question number 2. You and your sibling are lifting identical 50-pound boxes from the floor to the kitchen table. You lift yours in 2 seconds. Your sibling rips theirs up to the table in just 1 second. Who is using more power? Remember our race up the stairs and the mathematical relationship between power and time? And finally, question number 3. We talked about a specific type of energy that represents the capacity to do physical tasks, one that acts like a stored-up force ready to be unleashed. What kind of energy is like a compressed spring just waiting to bounce? Recall the most common form of energy we focus on in secondary physics. All right, let's see how you did. Excellent job locking in those concepts. For number 1, the answer is no. Pushing an unmoving truck means 0 displacement and therefore 0 work. For number 2, the faster person uses more power. Since power is work divided by time, less time means a higher power output. And for number 3, that coiled potential is mechanical energy. As you can see, science isn't just trapped in a textbook. It dictates literally every lift, push, and step you take. So the next time you help a friend move or carry in the groceries, will you just feel the exhaustion or will you actually calculate your joules and watts? Armed with the work energy theorem, you don't just have to sweat. You now have the power to understand the hidden mechanics of the universe.